Hello everyone. Today I will present the update made to GenPPI. Just to remember, GenPPI is a software written in Common Lisp compiled with SBCL to create complex networks of predicted proteins from tens or hundreds of genomes. Previously, its main limitation was the amount of RAM on your server, but in this new update it went from being single-core to multi-core, increasing speed and power to predict interactions. Now GenPPI is open source, you can go to GitHub to take a look at it, give ideas for improvements and modifications if you need more RAM or other. SBCL includes the whole core of libraries for each executable, and it explains the size of the software in megabytes. The new version also uses machine learning using random forests to create complex networks of predicted proteins. In order for the software not to be too heavy, in addition to downloading the new version of GenPPI, it is necessary to download the 3 model files, which will be used as training for the random forest. Let's wait for the 3 files to download before we continue. Ready, everything downloaded. With the model files in hand, I will move them to the directory where I tested with the first version of GenPPI and unzip them, creating model.dat. This file needs to be in the directory where I will use the program when using it with machine learning. To unzip, I will use the software already installed on my machine, 7-zip. If you don't have one, just a quick search on the web for your Linux distribution. To use it, it's very simple. Just follow the command 7zx one of the files. In this case I'll take 001, the software will unzip the 3 and join them into one, forming model.dat. Now, I'm creating a symbolic link to keep my file in one place, saving memory. Continuing with the example of the first version of GenPPI so that we can see the differences, I will use the genome of Buchnera athidicula. I will be running the software in another directory to save the versions and always have the results of other interactions. There are a lot of possible parameters and combinations of these on running GenPPI. I recommend you start simple. Now I'm not going to use machine learning to show the difference I've already made within GenPPI. Checking the results and comparing with the first version, we were able to notice that it is managing to identify much more PPI, both CN and PP. Taking bot_ak as an example, we had 300 PPI by CN and 42 PPI by PP. Now in version 1.5 without machine learning we get 2,330 PPI by CN and 5,810 PPI by PP. Now let's do the same process but using machine learning. Let's follow the same steps but we will put the ML parameter. When we run GenPPI with this parameter, the random forest program first reads the model from the model.dat file and then predicts the interactions, so it ends up taking a little longer. This is normal. Starting to analyze. Okay, it's over. Now let's look at the data and see if it was worth taking a little longer. Now, let's compare the results of the 3 tests carried out. The difference between using machine learning and not using it is clear, creating almost 10 times more PPIs. With machine learning we achieved 2,683 PPI by CN and 74,119 PPI by PP. Returning to the previous ones, the difference in the ML parameter is huge. We can see in GenPPI the interaction network formed, which if you remember the first one was very small compared to this one. Now I will calculate, for example, the bridging centrality for this network. I can ask GenPPI, for example, to rank these nodes according to the bridging centrality measure. Let's see that. So, now we have the top node according to bridging centrality in dark green color. Here we can see the node that has the most interaction, and that could possibly be an important protein. And see the data also referring to the same calculation and others with more information. Looking through GenPPI, we can see the network of interactions even better, as the proteins are more grouped, with the majority being. Now I will calculate again the bridging centrality for this network. And ask to rank these nodes according to the bridging centrality measure. Let's see that. So, now we have the top node according to bridging centrality in dark green color. We can see that now in GenPPI the number of nodes is very large. Also due to the number of interactions, helping more in the discovery of important proteins. And with the help of GenPPI with my plugin, Bridge Centrality, we have a very good chance of discovering much more than I am showing and with little known genomes. For an initial explanation about our software GenPPI, I think that's enough. Please, access GitHub and look for GenPPI. You will find all the binaries necessary to execute our software in some tutorials, including tutorials for the operating system Windows. If you need some adjustment in the binaries, please contact me. For now, that's all, folks. Thank you for your attention. Please use our software. By using our software, you have the power to decide how many genomes and which species you will use to answer your scientific question. Thank you and cheers.